Hi everyone, welcome to this episode of Keipert Labs. Today we continue our little mini-series on Newton's laws of motion. And today we're going to focus on Newton's second law. Okay, so far we've looked at Newton's first law and this concept that we summarize as inertia, or the tendency for an object to maintain its state of motion unless acted upon by an unbalanced force. So it will, if it's stationary, it will stay stationary. If it's at constant velocity, then that's what it'll do. But if it's acted upon by an unbalanced force, then it may speed up, slow down, or change direction. Okay, so they're all things that could happen if acted upon by an unbalanced force. But now Newton's second law is what is now describing about, okay, what happens when we have an unbalanced force? What happens to make this work? And also, how can we predict how much it's going to speed up, slow down, or change direction based on the nature of this force? Okay. So, all right. So here we go. So Newton's second law. It's actually it's a lot less wordy than the first one. And really, it's actually more mathematical, and it's summed up by a maths equation, which is F equals m times a. That's it. Now, obviously, it's not actually it, because now I have three letters in this maths equation. I haven't articulated what any of them are, how you use it, what it means, or anything. Okay, but it's just that in terms of its summary, F equals m times a, or we often, because you guys are a little bit more comfortable with maths than, say, a year 7 student, we can take out the time symbol here, the multiplying, and say F equals ma is Newton's second law. Okay, so hopefully what these letters mean should be fairly straightforward for you at the moment, but it shouldn't be a massive surprise here. Okay, so what we're talking about is F is the force. Now, before you get too hung up on writing that down, sorry if you did, I'm actually going to change this to talk about this idea of a net force, or an overall force is perhaps a slightly more everyday kind of phrase we might use. I'll explain why in a moment. M equals mass in kilograms, and so our force is in newtons. And then acceleration is a. That is 2 C's, by the way. I can spell. Okay, it's just this is not an overly fine pen. Okay, and acceleration in meters per second squared. Okay, so they're the units that we would have. So F equals ma. F is our net force, or overall force in newtons. M is mass in kilograms, and a is its acceleration. Okay, now what I'm going to do is slightly kind of over here, just in this space. I'm actually going to slightly rearrange this in a way that I think makes things a little bit easier to understand. Okay, so this is the one that I really want you to try and focus on remembering. Both of these, they're just rearranging the same formula, by the way. They're not fundamentally different. What I've done over here is I put a little net in here, just as a little, to remind us of what we're talking about, this idea of a net force. Again, I will explain that in a sec. But so, now we're saying that an object, so when we're talking about an unbalanced force, an object's acceleration depends on the net force that's acting on it, divided by the mass of the object. Okay, so the acceleration depends on how big the force is and the mass of the object. As the force gets bigger, acceleration gets bigger. As the mass gets bigger, acceleration gets smaller. Okay, if we keep making this number bigger and bigger, but we don't change the force, then the acceleration that will happen will be smaller. Okay, so I'll keep those there, and I'll see if I can use this space underneath. There's a little bit of the canvas for now. And then to unpack this concept of the net force. The other term that we might use is the resultant force. Okay, is a slightly more physicsy kind of term for it. This idea of, okay, let's say we have an object that, so it's hanging from a, let's say we've kind of got a pulley that's over here. All right, so we've got a rope here and then you've got Joe Blow over here that's pulling on this rope. Now, if I look at this object, there's two forces acting on this object at the moment. The first one is gravity that's pulling that object down. The second one, which goes in the opposite direction, is what we would call the tension of the rope. The tension that's then being as this person is pulling on that rope, then that we're seeing that this object will travel upwards. Okay, and so what we have here is that we've got two forces going on. So we've got the force of gravity and the force of the tension and the pulling the force that's being put on it by the person on the other end. And so if we're trying to work out the acceleration or how this object's motion will change, we need to account for how these forces all kind of cancel each other out, or how they kind of work out. Because if these two forces are the same, like before this person actually does anything, then this box will stay still, because the tension holding the box up is the same as the force of gravity that's pulling it down. That's why it's not going up or down. Okay, and so we don't say there's no force on the object, but we would say there are balanced forces. Okay, so because we've got balanced force, then what we would say is the net force equals 0 in this situation. Okay, because if the forces are balanced, if the two things balance each other out, then overall that we have as a net force of 0. We've got no overall motion that's happening there. But as soon as this person starts to pull, and then the tension, the pull of the rope gets bigger than gravity, then all of a sudden we have unbalanced forces, and the net force is not equal to 0 anymore. The net force is bigger from the tension than it is from the gravity, and so the box moves up. You know, that's the whole idea of a pulley, is this idea of actually allowing you to lift heavy objects against gravity. And it also, because of the nature of the pulley, you actually get a force benefit. It's actually easier to pull it like this than it would be just to hold on to. If you could hold on to this rope and pull up, you actually, it's easier. Okay, so this idea of the net force is the force left over. So I'll say leftover force once other forces are accounted for / cancelled out. Okay, so once we've kind of we've accounted for all the different things that might be on an object, we see what's left, okay, and which direction is that force going in, because that's ultimately going to decide where that object moves. Okay, so like I said, this is a maths equation. It's not just an expression in words, so I'll demonstrate to you how this works, okay, and then we'll probably leave it there. Okay, so I'm going to use this version of the formula because I think that logically you will get a bit more understanding out of thinking about it like this, because as you can see, you know, as the force gets bigger, acceleration gets bigger. As the mass gets bigger, acceleration gets smaller. Okay, that's the kind of idea that I want you to work with. Okay, so if I've got a force of 100 newtons pushing on a box that has a mass of 0.1 kilograms, and then we want to say, okay, well, what's its acceleration going to be? You know, so it's going to accelerate, okay, because we're putting a force on it, and we just want to work out, okay, well, how much does it accelerate? If you were to track that, how much would its velocity be changing? Okay, so its acceleration is equal to the force divided by the mass. Okay, so a force of 100 newtons over a 0.100 kilogram box. What you're going to see very shortly is that we've put an incredibly large force on a rather light object, so it's going to go traveling very, very fast. 1,000 meters per second squared is going to be its acceleration once we do that calculation. Okay, so that's a little bit obscene as far as that box is practically leaving the atmosphere, let's be honest. Okay, but to illustrate the point. Okay, so now we're going to say, all right, well, so we have a car that has a mass of 1,000 kilograms, 1 ton, is accelerated by it has an acceleration of 2 meters per second squared. What is the force that's being applied? The net force. Okay, so we're substituting into this formula. We know A and we know M, but we don't know F. So we're going to substitute in. So we've got A equals F over M. I'll put in the net just to keep the terminology that we're sticking with. Okay, so we've got an acceleration of 2 meters per second squared is equal to our mystery force, net force, divided by 1,000 kilograms. Okay, so in order to get, I want F net to be my subject, so I'm going to multiply both sides by 1,000. So I'm going to get 2 times 1,000, or a force of 2,000 newtons. And that's my answer. Okay, so that you can see that there's quite a large force that's needed to get a big car to accelerate at a fairly small acceleration. Okay, that's one reason why we have to burn so much petrol, why the car has to work so hard to get itself moving, and then in order to accelerate like that. Okay, but so you can see that in both of these situations that we've used this same formula, we've substituted in what we know to calculate the thing that we don't. Okay, so that sums up Newton's second law. All right, thanks very much for watching. Bye for now.